Okay, this is number 22, again in section 5.3 exercises, and we are given our matrix equation, right? This is, actually I didn't write the little vector above, the little arrow, just because everything is in bold, and so there's nothing to distinguish what's bold and what's not, right? So all my x's are actually bold. So we have x prime equals, right? This is our ax, where a is our coefficient matrix, right? Here's our matrix equation, and we're given the solutions of this matrix equation, which are vector functions or vector matrices. Notice, right, they're 2 by 1 solutions, and the question in the book is asking for us to first verify that these two vector functions are solutions to the system, and that's pretty easy. Number 2, we're going to use the Wronskian, right, this concept of Wronskian, to show that our vector functions are linearly independent, right, where the Wronskian is really just finding the determinant of our matrix. And finally, we want to write and obviously find the general solution to this matrix equation, or matrix differential equation specifically. Okay, so let's start with number 1. And number 1 is obviously verifying, right, that these vector functions are in fact solutions to the system. So we basically want to prove or show two things. We want to show that okay, our general equation is x prime equals ax, right, where a is my coefficient matrix above, and right here's my coefficient matrix, right? But this x represents that's really x bold, so that really represents the solutions. So we have two solutions given, so x1 and x2. So separately, we're going to do we're going to find x1, right, and then we're going to take the derivative, and then we're going to take our a, and then we're going to multiply that to our x1, and similarly x2, take the derivative, write our coefficient matrix, and then we're going to multiply our 2 by 2 matrix by our vector function x2. So this is what I want to show in order to verify that this is true. Okay, so let's I'll just call this okay, so we have left hand side and right hand side. And so I'll actually just do this part. It's very easy. And then I'll let you guys do this part. It's, again, just matrix multiplication practice. Okay, so let's start with this guy. So x1 prime, well, what's my x1? My x1 is e to the 3t, 3e to the 3t, right? That's what's given. And I'm going to take the derivative of it. This is really nice. I mean, the derivative is really just of this matrix is just the derivative of the entries. So this is 3e to the 3t, and let's see, chain rule 9e to the 3t. Okay, so that is my left-hand side. Okay, so let's see if our right-hand side is equivalent. So a times x1. So there's no differentiating in this part because there's no primes. So I'm just going to take my a, which is negative 3, 2, negative 3, 4, and times my x1, which is given, and that's e to the 3t, 9e to the 3t. Again, a, x1. And again, just matrix multiplication. And here, remember the order of these matrices. This guy is a 2 by 2, and this guy is 2 rows, 1 column, so it's going to be 2 by 1. And these guys, right, the inner guys have to match in order for the matrix to be defined, the resulting matrix. So here we are going to get a 2 by 1, right, where I have, right, this is rows and this is columns. So 2 rows, 1 column. Okay, so I'll just write that in. And again, row times column, row times column. So I'm going to get, let's see, I'm going to get negative 3e to the 3t plus 6e to the 3t, negative 3e to the 3t plus 12e to the 3t. And I can simplify this a little bit, right? I can say, right, there's, I mean, e to the t, or e to the 3t, e to the 3t. So I get, excuse me, we get 3e to the 3t and 9e to the 3t. So this is equal to our right hand side. And does that match? And it does, right? This is therefore x1, so you can say, let's just write it in words. Therefore, x1 is a solution to the matrix equation above. Okay, so x2 is very similar to this. You should, I mean, it should work because it says verify. Okay, so the next part, number 2, is to use the Wronskian to show that our solutions are in fact linearly independent. Okay, so if we set up our Wronskian, so that's going to be big W of t, and we have a 2 by 2 matrix, but we are not going to use the coefficient matrix, right? The coefficient matrix is obviously a matrix with only coefficients. We want our actual functions of t, the solutions. So this is one column and this is the other column. So let's see, let's use some green. So that's one, right? And I don't know, blue. So green and blue. And so, oops, I'm gonna write in my green is e to the 3t and 3e to the 3t, right? That's the one solution, x1, and the other solution is 2e to the negative 2t and e to the negative 2t. And the vertical bars, right? These mean the determinant. Find the determinant of a matrix. You can also write this as determinant, right, of you know, the same guys, right, the green and the blue. I'm just going to use the vertical bars since the book uses the vertical bars. Right, this is not absolute value because it's not of a number, it's an actual matrix. And this is a nice 2 by 2 matrix, so we know that, let's see, let me make this a little bit bigger. Okay, so we know that the determinant of a matrix A is AD minus BC, right? If A is A, B, C, D, right? Multiply those, and then find the difference. So if we use that, our W of T is going to be, let's see, e to the 3t times e to the negative 2t minus 3e to the 3t times 2e to the negative 2t. And, well, right, AD minus BC, and then this is just algebra. E to the t, and what do we have? Minus 6 e to the t, and right, that's really 1 e to the t, so we get negative 5 e to the t, which is not 0, and it's not 0, so that means that they're linearly independent. If it was 0, then our solutions would be dependent, so we can derive one from the other. So that's it for number 2. And let's see if I can do number 3. It's not too bad actually. Let's see. Number 3. Oops. Is okay. Write the general solution. Okay. So 3. So let's write the general solution of this matrix differential equation. So remember the general solution is x. So I'll write the bold here. So x of t equals, so c1 x1 bold, right, plus c2 x2 bold. And now we have our x1 and our x2, so we just write that in. So I write big, so I'm going to move this over. So we have c1 times x1. Well, I mean, x1 was given. Let's see, did I call that to be consistent. I made it green, so e to the 3t, 3e to the 3t, plus, right, C2, this is a general solution. We're not finding the particular solution because we're not giving initial conditions. 2e to the negative 2t, e to the negative 2t. I mean, technically we could have done part 3 in before part 2, but I mean, that's fine. It's nice that you do it at 3 because you do want to verify that the solutions are linearly independent. Because if there isn't, then you really don't, this is not the solution. And let's see, okay, let's do some matrix multiplication and scalar multiplication, actually. So, right, this guy is C1 e to the 3t, C1, 3, well, actually, even easier, 3 C1, looks a little cleaner, e to the 3t plus 2c2 e to the negative 2t, c2 e to the negative 2t, and actually just matrix addition. I think I said multiplication, but we're not multiplying because there's my operation. Okay, so c1 e to the 3t plus 2c2 e to the negative 2t, and similarly 3c1 e to the 3t plus c2 e to the negative 2t, and we are done. That is our x of t, x bold, or t, our general solution to this matrix equation. So hopefully that makes sense, and it's a combination of you know, the whole section. It's nice, you know, we're using obviously matrices. We are using the Wronskian. We're looking back at linearly independent and what that means in terms of vectors. So it's a nice review as well. If you have any questions, I'm feeling a lot better. Still a little bit tired, but a lot better. So feel free to, you're not bothering me. Please ask me questions, and I will see you guys in the next video.